welcome back to Wireless Future. My name is Eric Larsson, and I'm here with my colleague Emil Björnsson, as always. Hello, Emil.
Hello. How are you?
Good. How are you? How are things in Stockholm this morning?
It's great. And to see the sun in the morning again.
Yeah, the sun in the morning. I mean, it's progressively getting brighter, at least in the morning, because up here it's been very dark throughout the entire December, and of course partly so also in January. So now, Emil, you are in the spotlight again with your new book, Introduction to Multiple Antenna Communications and Reconfigurable Surfaces, written together with Özlem Demir, and that came out last year, 2024. And this is a book that is intended to teach to a fairly wide audience, I believe, of students and engineers, the foundations of wireless communications and particularly multiple antenna wireless communications. And it's a pretty, let's say, heavy piece. It has, it has 683 pages. Wow. So how could a student ever read anything with 683 pages? But then I figured I actually got a thicker one, the Harry Potter with a phoenix, and that one's got 993 pages. Of course, no formulas or plots or anything, but still a massive amount of text. So how did this book, Emil, come about? And I mean, given the market, given the fact that there are already quite a few wireless books out there on the market, and of course also books on MIMO technology in particular. So how did this book come about, and why did you decide to write another one?
Right. Yeah, that's many very good questions that I've asked myself as well. So I think part of the answer is that I like writing and explaining things. And when I'm writing, I also understand and put the pieces together better. So that's is an important thing. But
that's a very good answer and a very good point, in fact. I mean, I think we both of us like writing. And for me, writing has always been a way of thinking and structuring thoughts, and by explaining something, you also develop a deeper understanding yourself. There's a saying that the best way, one way to learn something is to read. The next best way to learn is to read and work with problems and exercises and test yourself. And the really best way of learning is to read and work with the problems and tests and all of that, and to teach the material to someone else. So that's truly impressive. But I believe for you, this is number what? I lost count. In fact, students come and then I say, well, this ought to be well known. You should check the book by Emil Björnsson. And then they always ask back, so which one? And then I was like, well, he's got like 1, 2, 3, 4, or maybe 5. I don't know. There is one on MIMO. There's another one on cell-free. There's one on resource allocation. So this is now number, which one in the series?
Yeah, I guess it's number 4 then.
Oh, it's number 4. Yeah.
Right.
So how did this come about, this writing project?
I think what typically happens in science is that a topic evolves over a fairly long period of time. And then in the beginning of an area, when it starts to get a bit mature, people write elementary textbooks and they start to be used at the universities and so on. And then for everyone who wants to write another book, they need to do, as I did with those other books you mentioned, write something that is more about what has been done in the research in the last 5 or 10 years as a more advanced course on the topic, maybe directed towards last year master students or PhD students and so. And I think a good example of this is also your red book here on Fundamentals of Massive MIMO. It's not capturing necessarily all of the fundamentals, but it captures one very recent type of technology that we have in 5G, Massive MIMO. It's focusing on these type of things. And so for that reason, there might not be a good reason to write something that would compete with these very classical textbooks. On the other hand, a classical textbook like Fundamentals of Wireless Communication, it came out in 2005 and covers a lot of nice things around MIMO, but in 20 years' time, of course, certain things become a bit outdated. there are some new fundamentals that should be covered together with the classical ones. There are some old fundamentals that are not so important anymore. And I felt that now is the right time to sort of write a new introduction book that can be used instead of the fundamental ones that came out 20 years ago.
Yeah, and it covers has a much wider scope of coverage as compared to, I mean, you mentioned our Fundamentals of Massive MIMO book, for example. But I think your book covers a lot of more basic fundamentals around wireless propagation and point-to-point MIMO and fading channels, and also some more niche topics like reconfigurable surfaces. There is a whole chapter, in fact, about that.
Right.
This book, I'm the privileged owner of a hard copy that you sent me the other month, but I also understood that you could, in fact, download this book for free from the publisher's website. And if in the preface here it's written that the work will be available online with open access, governed by Creative Commons license CC by BYNC. So the BYNC license, I think I know the BYOB means bring your own beer, but BYNC means beer.
So
I think the NC stands for non-commercial use or something of that sort, right? Which I suppose pertains to the actual text itself, not to what's written in there. I mean, nothing should prevent an engineer from reading and learning the material in your book and then building a wireless standard or system around that knowledge. But the text itself, to my understanding, could be in principle, could it be redistributed? I mean, is it like allowed to reshare the PDF then and have...
Exactly. So what this license means is that I'm still sort of the formal copyright owner, but anyone can download this PDF and it's available from the publisher, nowpublishers.com, for example. But anyone can download it, redistribute them as they like. They can even like adapt and modify things and then redistribute it in other ways in a non-commercial way, as long as they give attribution to us as being the original writers of the content.
That's right. Okay, great. So what are the unique selling points of your book? If you were to summarize, like, what are the unique aspects now comparing it to like the wide body of textbooks already available in the field, not necessarily to the specific book, although I would think that insofar, and I know for a fact you do discuss massive MIMO technology here, so for me then the natural comparison would be our own Fundamentals of Massive MIMO that I'm sure everybody is familiar with, but yours is a lot broader, obviously. And what are the unique selling points or unique aspects of the exposition of the material that you have, Emil?
Right. So the way that this book first came to life was that I was going to give a course on multiple antenna communications, and then a big portion of the course was based on your red books on Fundamentals of Massive MIMO, but I was also thinking that I would like to cover some of the fundamentals that are more general, like single-user MIMO or other kinds of multi-user MIMO forms that are good to know before or in addition to the specific kind of it that is used in 5G now. And then I started to first use some pieces of other textbooks, realized that is not a good way of having a course to ask students to look a little bit in different textbooks and then have one main textbook. So then I wrote some text myself, and that text evolved from year to year into 50 pages, 100 pages, 200, 300, and so on. And then after a while, I stopped giving this course, and I thought, should I either throw away all the content or should I give it away to other people to read it somehow, because I was kind of proud of it, and that was when I tried to consolidate. Okay, if I should write something here and finish it off, what should be the target from it? And I think I wanted to cover all the things I think is important for people if they will be part of doing development or research into future wireless systems. Because MIMO will be there at the physical layer regardless. So if you're going to work on the physical layer, of course, you need to know a lot of different things, and I want try to put all of those things into it, both in theory and with from practical examples. But also, if you will work with other layers in the system, scheduling algorithms and resource allocations, all the type of things will eventually boil down to also understanding how the physical layer behaves. So I try to cover all those type of things, use the latest terminology and so on.
But that's a great point indeed. I mean, because the true limitations of any wireless system are really at the physical layer. I mean, you got bad protocols. Well, come up with a better protocol. You got bad software. Well, just rewrite the software, something better. But you can't mess. The physics is what it is. So you can't mess with the physical limits. So even if you don't work with like physical layer development, then understanding the limitations imposed by the physical layer is super important. So I love that point. And I think I appreciate, I mean, this is at least, it sounds like this is at least a 10-year effort to put together, and typically that's how books come along, that they grow organically from teaching a course a number of times, and then over time acquiring material, developing material, and writing and rewriting again maybe, and now we seem to be finished.
Yes, exactly. And that was a lot of hard work to really finish these type of things. And then
it's a lot of hard work.
You have spent this time, I wanted to maximize the readership, and I understand that I will not compete with Harry Potter in terms of selling huge amount of copies. I guess it is competing against the Bible with being the most sold book around the world. So I realized that the most impact I could make with my teaching is to give away this kind of book for free. Then you can still buy these nicely printed copies. Of course, those are not free, but the PDF version is free. And so far, there's 12,000 downloads of the full PDF from the publisher website.
Wow, that's a lot. 12,000. That's really a lot, I think, for downloads. Yeah. So let's get to the back to my questions on the unique selling points that you have, Emil, with the exposition in your book.
Right. So the one thing that I particularly tried to do was to identify some things that I felt are missing in other textbooks, and I've now identified like 10 different concepts that you can sometimes find in textbooks but are not that visible, but I think they're really important to know if you would be working on these things in your career. So I try to weave all of those things into the entire text in an organic manner.
Yeah, absolutely. So let's see if I'll agree with you or not. So let's go.
Right. So the first thing has to do with physical quantities. So what are the actual power values that we are seeing in wireless communication, both at transmitter side and the receiver side? What is a noise variance in terms of milliwatts or whatever watt numbers it's going to be? And what is the path losses? And the reason that I bring this up is that a lot of textbooks wants to make the formulas simple for their readers, so they are normalizing things. They say, well, the noise variance is 1, or the path loss is 1, and we only consider the randomness around that value. And in some cases, or in many cases, this can actually be done with no loss of generality, as we are saying, because we're considering ratios between 2-3 different variables. So the important thing is to specify the ratio and not the different values of them. But if we also are never learning what the true numbers are, then I see that a risk that engineers have no real gut feeling. Is the transmit power, is it in watts? Is it in milliwatts? What is it?
So are you advocating that when you give like signal models that the noise should have like some special notation for the noise power, for example, rather than to normalizing the noise to have unit power?
Yes.
Like in many...
So what we start with already in the first chapter is to say, okay, you have a transmit power, it has a particular notation. We have a propagation loss, that is a parameter beta that reduces the transmit power to the received power, and then there is a noise variance, sigma square. And then in all of the equations you often get these things, then transmit power multiply with the attenuation, this beta parameter, divided by the noise variance, and that is what shows up. And in principle you can give that just one name, call it SNR, and then only specify that number, but we give examples already in the beginning about what are these different numbers, because they can have huge number ranges.
Yeah, they absolutely can. I mean, this might be one of the issues where I'm not sure I completely agree with you, because I tend to think that you should always minimize the amount of extra notation that you bring to the exposition, and therefore, to me, it always made sense to normalize models so that the noise variance is equal to 1, for example, or noise, whatever power means. But with a stochastic model, I mean, the second order moment is the variance. We call the power is 1. And then now, needless to say, we should teach the students to do elementary link budget calculations. And if they can do elementary link budget calculations, they can always just rescale the model to fit like physical reality. But I think that's the one that we probably do agree on, that performing an elementary link budget calculation is a super important skill, and particularly when producing like numerical examples for dissertations and papers, to make sure that the numbers put in there make good physical sense.
Yeah, no, exactly. I agree with that as well. I see the also educational or pedagogical value of normalizing and removing some somewhat unnecessary notations in some parts of books in order to focus on the essential, try to teach there, but also being able to do this kind of link budget analysis. And I think the reason that I wanted to make this kind of points already in the beginning of the book was that I see in reality in science that sometimes people have missed this whole link budget thing. It seems like there is an ability of getting past courses in elementary wireless communications without learning these things properly, and then there are a number of mistakes that can be made that I've been seeing in review processes. I think one of these things has to do with wireless power transfer. So normally when we are transmitting power to a data receiver, then you receive an incredibly small amount of energy, but you compare it with an incredibly small noise variance, and therefore the ratio, the signal to noise ratio, can be fairly big and you can communicate quickly. But if you do wireless power transfer, so you like to harvest energy from a wireless transmission, then it's the actual amount of received signal power that matters, not the noise power. And if you then are not normalizing things correctly, you can come to very strange conclusions there. And I've been reviewing multiple papers where these are done, and people believe that you can do wireless power transfer over huge distances just because the noise variance was one.
Yeah, I can imagine. I mean, it's a lot of garbage that's being submitted to these journals.
Yeah.
But I would totally agree. I mean, but I would still maintain that link budget calculations are equally important for communication links and for power wireless power transferring links. It says with a wireless power transfer, and then the noise becomes unimportant. All what matters is like how much power you can get across. So
right.
Another thing that we
So there's one more example there that I can mention since we're on the topic. So when people are considering like relays, repeaters, or reconfigurable intelligent surfaces, then you get like a so-called double path loss. You get the path loss from one point to this RAS, and then multiply with the path loss to another RAS. And then you usually compare this with the single path loss from the transmitter directly to the receiver through some scattering environment. And if you don't have the right scaling on your path loss formulas, then you get a strange effects here, because you have the multiplication twice at one place and just one in the other paths.
Yeah, absolutely. I mean, I'm totally on board with you here that when you work with scattering models, like be it a scattering object in a channel or be it an atom in a wreath or something, then it becomes even more important that you actually use a physically valid representation for the propagation and for the path loss that enters into your link budget. And so that's a totally important point. And, it might be actually a good way of starting off. I'm thinking now that rather than starting off teaching wireless comms by introducing modulation formats and QAM and waveforms and spectral densities and all of that, just start with a link budget calculation and develop some basic intuition for an understanding for range and signal to noise ratio and coverage and so on. So another thing that we've been debating a bit, I think, in the past, back and forth, Emil, you and me, and that I know that you have your take on here in your book, is what metrics to use to evaluate the performance of a wireless link. So would you want to deliver your view on that?
Right. So I think that many people who will be reading this book, and if they're learning this topic for the first time, they have previously taken a course on digital communications. And in such books, which are also often very old, they were considering the bit error rate or ratio as the main performance metric. And they start with uncoded transmission, then they do some channel coding a little bit on that, but it's still consider bit error ratios as the metric. And then they come to books like ours, including, I guess, your red book, that is considering the channel capacity. And they get a bit confused about what is the relationship between these things? Which of these metrics is the most important one to have? And the entire book is essentially considering different forms of capacity data rate formulas, but we spent some time in the beginning trying to motivate how its relationships is to the bit error rates.
Right. I think this is a good point. I think it might depend on from what angle you teach the digital comms. I mean, if you start from the information theoretic angle, then you would naturally introduce capacity as a metric. If you start from a more like detection theory framework, sending BPSK or QPSK symbols and then thresholding and detecting computing, you would end up with probability of error for uncoded transmission. But I think your basic point here, which I completely concur, is that capacity is a much more natural metric. As soon as we have reasonably long blocks, I mean, we know that state-of-the-art channel coding can bring us almost to the theoretical limit dictated by the channel capacity. And therefore, my view would be that a basic course in communications of any sort, wireless or digital, should start with introducing and building an intuition for the Shannon-Hartley formula, the B log to 1 plus P over B I naught, basically, which is the capacity, rather than fussing with bit error probability for particular constellations, QPSK or QAM or something, and starting from that angle.
Right. And I think the thing that is really matters in the practical system would be some kind of block error probability. So and then you are using some kind of adaptive modulation and coding where you have a particular block length, you choose your modulation, your coding scheme in order to get a particular error probability in that one. And that is the most realistic metric perhaps, but it's enormously complicated to analyze in any mathematical sense.
Yeah, that's true. But also, I mean, a lot of practical systems, they use some form of incremental redundancy with or hybrid ARQ with incremental redundancy, so that if a packet fails, then don't retransmit the packet, but rather transmit additional parity bits. And to model the performance of such a link, capacity is still a very good metric. I mean, so
exactly, that is the point we're trying to make in the book, that we can abstract away a lot of complicated things and get work with capacity, and then that formula is really important. And
and as long as, I mean, you have reasonably long blocks, whatever that means, maybe 10,000 bits or something, then these capacity expressions are extremely good proxies for the actual link performance that you get with practical state-of-the-art modulation and coding. I mean, you basically compute a capacity limit, and then you add like a dB or possibly a couple of dB margin, and you are at the point where practical schemes deliver. So
right, but then there is not only one capacity concept. So as soon as you start to work with fading channels, there is the thing we normally call just capacity. Then there is the outage capacity or outage probability, and then there is the ergodic capacity. And we try to talk a bit about these different things. I mean, we cover the formulas, but also when will you get the different situations? And it's really a question of how many realizations of a channel will you have when you are transmitting this data block. Is there only one? And that channel on both transmitter and receiver, you use the normal capacity metric.
Yeah.
If there is only one, but you don't know it's a transmitter, you work with the outage capacity. And if there are many of them, and doesn't matter if you know them on transmitter or not, you can use their Gauge capacity.
Yeah. So you cover basically all the combination of cases that the code word sees a single realization of the randomness, the channel randomness, the fading randomness, or many realizations of the fading randomness, versus the transmitter knows or doesn't know the realizations of the fading and so on.
Right. And of course, all of those formulas, or many of them, exist in other textbooks as well. But we try to give this kind of text, this context about when to use the different ones, which I feel is missing in other places.
Yeah, it's totally important, I think, to build understanding for exactly that, when to use which one for modeling of performance. All right, so maybe let's move on to other things that are unique.
So another thing that I tried to weave into this book is classical array signal processing theory, which is describing how the shape of an antenna array is also determining the physical shapes of beams. And this topic comes from array signal processing from the beginning, and then for a long time people were only considering MIMO for line of sight scenarios where the beams have this kind of shapes. And then over time, we have been considering more general cases and just consider arbitrary channels and fading environment and so on. And then I feel this physical structure is often being lost in at least many cases. And therefore, I think it's important to cover these things, even if they are mostly important in line of sight scenarios.
Yeah, I was going to say, I might not completely share your view here, because isn't it that multi-user MIMO beamforming, of course in its preferred form, we use uplink pilots to get the channel state information, but irrespective of how channel state information is obtained, multi-user MIMO beamforming is totally agnostic to what a propagation channel looks like or whatever the array topology looks like. And to me, that's always been like one of the central themes of modern MIMO processing, that it doesn't quite matter whether the array is in line of sight or whether it's uniform linear. It doesn't matter what these air quotes beams look like. Whether they are really like textbook style, free space line of sight, kind of droplet shaped, or not. But I certainly could agree on the fact that it is useful, and we should make sure to teach students a basic understanding for what does a beam look like if you are in free space line of sight and you got the uniform linear array shooting in some particular direction. What will the beam shape or the angular distribution of power look like, even though this in the end really doesn't matter for modern multi-user MIMO beamforming? Would you concur on that, or what would you say?
To a large extent, I agree with you that we can operate the system without having to rely on any particular channel models and with the kind of channel estimation you're describing. Then at the end of the day, when you will be evaluating your performance in the system, then the channel models that are underneath are going to determine what you can achieve, and then some of the physics will still be there unless you have some kind of ideal isotropic scattering environment. And take an example: you have an antenna array, you deploy uniform linear array on the rooftop, and then it turns out that it's deployed so all of the users are always to the right of this one. There is very seldom anyone to the left. Then this has some physical results out of it, some losses, that half of your dimensions that the antenna array can transmit in will be towards the right and half to the left, and you will lose something from this. And if you don't understand those basic phenomena, then it is hard to understand those concepts as well.
Yeah, no, fair enough. That point is well taken. And obviously in performance evaluation, I think we got to distinguish between understanding the basic operational principles of a multi-user MIMO beamforming algorithm on one hand, and on the other hand, using a specific model in performance evaluation through numerical simulations. And obviously when you run numerical simulations, you got to put a model in there, and you could then, if you're on line of sight, I mean, it's easy. If you're in non-line of sight, you got to use something more advanced with clusters of scattering points and all of that. So
right.
And for that to do that, I mean, you do need a physical understanding for what propagation looks like in line of sight, at least for a uniform linear or planar array like you have in your book.
Yeah, and there will be still a lot of line of sight dominant scenarios in the future, millimeter wave terahertz, satellite communications, in these kind of cases. So that's why I think it's important to have that knowledge as well, even if more recent textbooks might be focusing on just arbitrary random channels.
Yeah, no, I totally agree that it is. And we're getting back to this point where I think we started the conversation, that having an adequate understanding for the physics and the basic physical phenomena is super important. And the really simplest, most basic case to start with wireless propagation is line of sight with a uniform linear array. So I totally agree. I mean, that should be there in any serious wireless course. They should be there,
right,
as an element.
And one part that we also throw in here, because you very seldom find in textbook, is the uniform planar arrays, because that is what we usually have on a lot of at least cellular base stations. So bringing the basic formulas from some kind of reference sense into the textbook is something we also made sure to do.
Yeah, I agree. I mean, in practice, you probably don't have, you got planar arrays rather than linear. I mean, the linear is a special case where you just get like a single stripe of patches that sit on a line. Absolutely. So what else in propagation do you think is important, and what do you teach in your book? I mean, there's this one thing is this with polarization that I think you discuss at some depth, whereas a lot of other books make no mention of. I think particularly in our fundamentals book, we do not discuss at all. We do talk about line of sight a bit, but we don't talk about polarization at all, as that I can remember.
Yeah, no, polarization is this. It's this topic that is very important for practitioners, and it has been that for a very long time, but it is not often covered in my textbooks. That's why we have been placing it both in the line of sight and non-line of sight chapters of this book. And I mean, the basic thing is that a wave propagates in one direction, and then there are two dimensions that are orthogonal to that one, and the electrical field and the magnetic field is orthogonal to each other, and they can then oscillate in any of those two dimensions.
That's right.
And an antenna generates a signal which oscillates in one direction, and then the receive antenna is only seeing the electrical field and magnetic field that is oscillating in particular directions. And originally, this created issues because the user devices had like a single antenna, and it might be rotated, so it was not matched perfectly to the base stations. That's why they introduced dual polarized antennas at the base station, so you would transmit in two different polarizations, create some diversity against that kind of fading behaviors. And that was then something that was used for a long time ago, and nowadays, at least in 4G and 5G, we have dual polarized antennas in the user device as well, and this gives us extra dimensions. And in many cases, this like polarization dimension might be the first MIMO dimension that we actually utilize in real systems. So we never send one data stream, we send two, one in each polarization. And if our channel supports additional propagation paths, we don't get one extra dimension for that path. We typically get two, one for each of the polarizations.
That's actually a good point. I mean, so with dual polarized antennas, you mean like two small dipoles or patches that sit like orthogonally arranged, so one horizontal, one vertical, or maybe in practice they're rotated like this, 45 degrees rotated, and then you would be getting, at least in line of sight, you'd be getting like two independent streams. One from each polarization direction. Now, I tend to think that wave propagation as a subject is a difficult thing to start with. I mean, and I always like to think that pretty much all important, most important understanding of wave propagation can be obtained by analyzing a scalar field. So basically like an acoustic pressure source or acoustic sound propagation that follows the wave equation, the Helmholtz wave equation. And then now when we go from a scalar field like acoustics to electromagnetics, then we got this polarization thing with the E and H field, and we need to use tensors instead. Everything becomes like a lot more mathematically more complicated, but it adds very little extra understanding to wave propagation as such, beyond the fact that you got these two dual dimensions that you can more or less operate independently. I mean, if the antennas are properly tuned. But you're totally right that for a wireless engineer, understanding the basics of polarization is a super important thing. So I'm glad you covered that in your book, which I think is not so well covered in. I mean, obviously it's well covered in books on electromagnetics engineering, but it's usually not so well covered in books on physical layer wireless and digital communications technology.
Yeah, and there are some books that covers the channel modeling, and that very quickly becomes incomprehensibly complicated. But we try to stay away from those things and just try to basically explain these basic phenomena that I was mentioning and a few things around that, and keeping it as intuitive as possible.
Right, the basic phenomena, what are the implications of, given that we understand, let's say, scalar wave propagation, and going from scalar to electromagnetics, what are the implications of having this extra polarization dimension? What are the implications on the wireless comms layer? Interesting, great. So,
right. Then we move on. So now we have been talking about the first few chapters where we are talking mostly about single user transmissions, where you have multiple antennas, the transmitter and the receiver. And then we move on into the area where you have a base station and multiple users. And then multiple access becomes an important thing. And there, of course, multi-user MIMO is an aspect of it, and that is an improvement of classical multiple access schemes, for example, frequency division multiple access. But then in recent years, there has been a lot of fuss about NOMA, non-orthogonal multiple access.
NOMA.
There is tons of research on that topic, and some of them are probably useful, and some of them I get the sense that people have not fully understood the fundamentals there. So that is something we try to.
So, but Emil, just for clarity here, when you say NOMA, do you refer exclusively to power domain NOMA? I mean, superposition coding, essentially putting like one data stream on top of another, or do you also refer to other things? Because I've seen the term NOMA being used also in contexts like random access and collision resolution and activity detection of collisions and so on. But I guess here we are discussing now closed loop transmission of data on a data link. Is that so? Yeah.
So the other aspect that you were describing, those can be very valid, use cases. But now, if we just consider a closed loop, we want to evaluate the capacity when that different users could achieve, and we start with a case where the base station has one antenna and there are multiple users. And the simplest thing would be to just cut the frequency into pieces and give one piece to every user. And that would be some kind of orthogonal transmission where the users are not interfering with each other. And then NOMA is about giving the entire chunk of frequencies on the same time to all of the users, and then use this power domain, some successive interference cancellation methods in order to deal with interference. So you decode one.
So now importantly, in contrast to spatial multiplexing using beamforming and multiple antennas.
Yes.
So with like single antenna links.
Exactly. So right now there is only single antenna links. And even in these cases, there is a lot of claims about how NOMA allows you to deliver more data and so on that you can read about in papers. I hope what is written in those papers are correct. But the fundamental thing there is that what you can prove in both the uplink and the downlink is that the same sum rate that you can achieve, the maximum data rate among all the users that you can achieve with NOMA methods, you can achieve with frequency division multiple access as well. So we prove this in the elementary part of this chapter. And what benefit does NOMA bring you? Well, your so-called...
But Emil, just to be clear again, I mean, so this, I believe, is a well-known result in multi-user information theory, and it is valid under some additional condition. I think what you need here is that the power constraint is rather an energy constraint over the entire time frequency domain rather than a power constraint per subcarriers. That's so.
Yeah, the power constraint is measured in the time domain, so to say, and not in
sure. But I mean,
frequency.
It's an average rather than it's an average rather than an instantaneous power constraint that you need for this statement to be true. I think.
Yeah,
is that so?
And that is. I mean, in OFDM systems, that would then be that the power constraint is over all of the subcarriers at the same time. Yeah.
That's a good point. You know, with an OFDM system, you would have an average constraint naturally.
Yeah, exactly. So that is why that is a natural kind of thing. But I think the distinction then is that is not the constraints that sometimes are being used when people are demonstrating that NOMA is better than orthogonal access. They compare with some other implementations.
I think you compare apples to oranges, because then that would be like having a per subcarrier power constraint in OFDM, which kind of doesn't make any real sense.
Yeah, no, exactly. So then what is the benefit of NOMA in these kind of single antenna cases? Well, it allows you to take this sum rate and divide it between the users in a different way, in a more flexible way than you can do with traditional frequency division methods, where there's only one way of achieving the sum rate. But it is really playing with small details. And then when you introduce multiple antennas at the base station, you can send multiple beams to different users. So that makes the users' channels look more different. And then on top of that, you can still do successive interference cancellation methods. So you can do something, this kind of nonlinear processing on top of the whole thing. But then the whole concept of massive MIMO is usually meant to mean that you have a surplus of transmit antennas or antennas at the base station compared to number of users. And as soon as you have that, one can see that the extra benefit from this nonlinear NOMA-like processing is very small.
Yeah, it's very small. I mean, or is it even... I mean, my view would be that any advanced, at least future wireless system would definitely use MIMO in some form, probably massive MIMO with spatial multiplexing. And then it's not clear to me if there are actually any important cases where NOMA would deliver any appreciable gains, given that you already have spatial multiplexing, probably massive spatial multiplexing, and all things considered, I mean, taking into account the errors in the error propagation and the successive interference cancellation, taking into account the impact of imperfect channel state information and so on. Do you know that, Emil? I mean, can you give like an example of a case where you gain more than... I'm sure you could find corner cases, I mean, but the question is, would those arise in practice with any probability? Every user lined up in line of sight in the same angle. Okay, so spatial multiplexing obviously is of no use. You could gain a little bit by NOMA. If you have high enough SNR and long enough blocks, you could gain a little bit, there's no question. But the real question is like, well, would that ever happen? What is the likelihood of actually having that in reality?
Yeah. No, I mean, I fully agree with you. Then we try to not take a really clear stance in this chapter, but mainly explain the facts and the phenomena that are playing there, and what are the potential, typically quite small benefits of this nonlinear processing at successive interference cancellation, and then explaining the drawbacks. And you were saying air propagation in the decoding will be one issue. You create delays, and scheduling becomes more complicated because you need to pair the users together and send the blocks of data in parallel, and all those type of issues.
Yeah. Well, so it seemed like we agreed on that one, Emil. Yes. Shall we
Yes.
talk about something where we...
So a short one, which is going back to, I guess, last episode we were mentioning OFDM as being the de facto waveform that is being used in 4G and 5G and probably in 6G as well. And what I feel is that many textbooks, when they present OFDM, they just say, here is OFDM. And this is how we do it. And there is no like derivation behind it. And then one thing I discovered, maybe it was really well known, of course, but in the writing, I understood that if you have a channel over a large amount of spectrum, you will have a channel with multiple taps, so there would be some delays. It's been like an FIR filter. And then the simple way of dealing with this is, okay, I send a block, and then I decode that block and I send another block, and then we add a prefix to your transmission in order to make sure that the blocks becomes non-interfering with each other. And if you choose that this prefix is a cyclic one, then that is all you need in order to get OFDM as the optimal solution. And if you take the transmission over that entire block, you write it in a matrix form, it looks like a MIMO system. With the transmission is your multiple inputs over your block, all of the transmissions, and the outputs are what you receive. And then this whole thing is a MIMO channel. And then it's a circulant MIMO channel, which means that such channel matrices are diagonalized by the DFT matrix, and that means that the optimal way of transmitting actually turns into be sending your data in the frequency domain.
Yeah, I think mathematically what happens is that a block tuplets matrix is block diagonalized by a block DFT operator. So to me it seems that OFDM is probably 99% of the cases simply the way to go, full stop. And the one thing that might be worth mentioning, though, is that cyclic prefix seems to be the de facto standard today of how OFDM is implemented. Nothing prevents the implementation of OFDM with other types of prefixes. And also, typical implementations, to my understanding, but of course I don't know this because I don't know what goes into the actual products, and a lot of this is proprietary, but at least in the textbooks, the standard approach seems to be to discard the samples that are received during the cyclic prefix. But in fact, those samples also contain information. So the optimal receiver would listen to the OFDM symbol and to the cyclic prefix, and then perform over multiple symbols successively optimal joint, maximum likelihood decoding, which can give some gains, but it's probably not worth it because complexity reasons, but just to state that point.
Yeah. No, so the bottom line is that if you add a cyclic prefix and then you throw away what you receive there, then classical OFDM is the provably optimal way of transmitting of such a channel.
What you said about optimality, of course, assumes that you throw out whatever data samples are received during the prefix itself. Great. So I think we agreed again, Emil. We got to find something where we don't agree.
Right. So let's disagree about channel modeling a bit here then. One thing that I think people are often saying is that depending on what frequency range you're working on, you need different channel models. At lower frequencies, like sub 6 gigahertz, you work with Rayleigh fading, with a lot of scattering. And at high frequencies, say millimeter wave and terahertz, we work with geometric channels where you sum up a few propagation paths. And I will want to make the point that there is a common modeling for all the channels on all frequencies. And the main point from this is that, of course, the environment around transmitter and receiver is physically the same. There is the same object around there. So you can consider, from some kind of ray tracing perspective, you send out a wave, it will be bounced on a set of different objects, and then there will be some components reaching the receiver. And you can write your received signal as a summation over these different paths. Then one can discuss how many different paths you would have, but it will come from the same physical locations.
Absolutely. You're right, certainly right, that irrespective of the carrier frequency, the physical environment is the same wherever objects are out there. are the same. But I think what happens is that the scattering cross-section of these objects depend on frequency, and that's why the propagation differs when you move across different frequency bands.
Exactly.
But I will probably reiterate my previous point that isn't one of the main advantages of modern multi-user MIMO that it is algorithmically agnostic completely to whatever the propagation looks like and whatever the antenna array topology looks like. I mean, as long as you obtain channel state information at the transmitter, and one more time, the preferred way of doing this is in TDD using reciprocity, then you got your channel state information, and we don't care whether you got a line of sight, whether you got some scattering objects or not, or whether the scattering objects are strong or weak, or you just compute your beamformer, which means for single user is conjugate beamforming or maximum ratio combining or transmission. For multi-user, you apply your zero forcing or whatever versions of that, and that's it.
Yes, so I certainly agree with that. And then when you do your channel estimation, you might have some kind of prior information about the channel statistics, and when you evaluate your performance, there needs to be some kind of channel model. And my point is that regardless of what frequency you're at, you will probably have either a Rayschen or Rayleigh fading scenario with a substantial spatial correlation, and this correlation matrix will definitely depend on what frequency you're at, because some of these paths will be stronger relative to the others at lower frequencies and weaker at other frequencies, and so on. But the basic modeling is the same. It's just that the covariance matrix differs.
Absolutely, but that's a well taken point. I mean, so in principle, what you're saying is that we could get away with the same model for the physical propagation irrespective of carrier frequency. It's just that the parameters that enter into the model, like the cross section of the scatterer and so on, they will depend. In fact, I think they will depend heavily on the on the carrier frequency itself.
Yes,
exactly. I definitely like that one. Yeah, I mean, there's no reason to make a distinction in the modeling, on the fundamentals of the modeling part, whether this is sub 10 or millimeter wave or something else.
Great. So let's move on to a little bit of hardware then. So
hardware.
Yes, because the most of the book is talking about digital beamforming, which I still believe is the most important hardware implementation in the long run. But then when you are entering operation to new frequency bands, it might be hard initially to build digital beamforming architectures, and then people are considering analog and hybrid implementations. And
so are those still being considered? I mean, I thought that obviously at sub 10 frequencies, fully digital is the way to go, and the way the commercial products are built, to my understanding. But looking for instance at the millimeter wave bands around, let's say, 30 gigahertz, what does state-of-the-art hardware look like there? Do you know that, Emil? I mean, are there fully digital products, or are they built upon some sort of beam steering and hybrid beams?
Right. So I think what is used today is arrays of analog arrays, so to say. So you have a collection of analog beamforming arrays. This is also known as a subconnected hybrid beamforming.
Right.
So this is what is used today, and maybe
that's what's used for millimeter wave.
For millimeter waves.
Yeah.
And then maybe it will be changed to some other hardware architecture in the future. People are considering using metamaterials and other things instead of phase shifters, for example. But it's still on the roadmap for what people are considering what they are building.
Where's the hurdle? I mean, is this perceived like, is it cost that the actual circuits are just expensive, or is it power consumption so that the thing just gets too hot or burns too much electricity, or what are the limiting factors that still today makes us think about hybrid beamforming? For let's talk millimeter wave now.
I think that it's mainly cost and bulkiness, because when it comes to power consumption, then the phase shifters have quite some insertion losses as well, so there's a lot of heat dissipation in those ones, and that has been one of the hardware implementation issues in mobile phones, where you create a lot of heat.
Yeah, and if you create heat, I mean, in a mobile, that heat will impact the energy efficiency of the transmitter chain, I suppose, so that you'll also burn battery.
Yeah, but the main point I try to make here is that I want to explain the basics of digital and hybrid and analog beamforming. And my viewpoint from there is, when is it sufficient to use one of these simpler architectures? Because I feel that a lot of papers are saying, we would like to do digital beamforming, but we can't build it. So let's use something else, and then we pay the price. But I take this other direction. And what you can do with analog beamforming is to send a beam in one angular direction. And there are scenarios like line of sight, or when you have just one object that you can bounce your signal on to reach the receiver. If this is approximately how your channel looked like, well, then analog beamforming is enough.
But Emil, when you say analog beamforming, do you mean some sort of grid of beams where you can send the beam into 0 degrees or 1 degree or 2 degrees angle? Or do you mean an analog beamforming where you can actually continuously change the phase and adapt it to wherever that scattering point or receiving?
So I mean that on every antenna you transmit with the same power, but you can change the phase maybe continuously. But you can only send one signal at a time in one angular direction or with one.
Yeah, so one signal that gets multiplied with a unique phase shift for every antenna.
Yeah.
So basically you're restricting your beamforming vector to have unimodular components. That would be like analog. That I would concur with, that in a lot of cases you can get very far with that.
Yeah, so if you only want to send one data stream...
Yeah, for a single user stream. Yeah, for multi-user I would disagree. I mean, for multi-user I think that's you lose a lot, but for a single user, it brings me back to think back about equal gain combining versus maximum ratio combining. I think there's like a dB or something loss one compared to the others.
And then if you have a multi-user environment, or in general an environment with where you would like to send multiple beams, then it might be that the environment is still rather spatially sparse, meaning that, say that there are 4 objects that the signal will bounce upon and reach your receiver or receivers. And in that case, what you need to do is to transmit one beam towards each of these objects, and then for every user or for every data stream, you need to make some kind of linear combination of them, which you do in the digital domain. And this is what you can do with hybrid beamforming. So in those specific scenarios, hybrid beamforming will be enough.
Yeah. That I would agree. If the channel really looks like that, I mean, if you really have just a few strong scattering points, you'll always have clutter. But if that clutter is way below the radii cross section or the strength of this few scattering points, you could actually do something like that. This is an interesting thought. Then obviously there are all these issues like getting channel state information with a hybrid array and so on. Maybe we shouldn't go there today.
No. We only try to convey
so reality is not as simple. Reality is not as simple. I mean, it's again a very idealized, beautified picture of how the hybrid architectures could function.
Right. And then towards the end of the book, we feel that, okay, now if we have spent a lot of effort on working with communications, MIMO scenarios, then why not use these baselines to also do some other things? We have one chapter about localization and sensing, and it is kind of things that you find in other textbooks on localization and sensing, but we use some of the terminology from MIMO communication and we build upon what we have there. But one thing we try to do that I see now when people in MIMO communication start to work with sensing is to explain the relationship between fading models for communications and this kind of radar cross-section models that are used in radar.
But aren't they the same, Emil? I mean, Rayleigh fading and a swirling. Is it swirling 1 or swirling 2? There are 2 different types, and I can never remember which one is a Rayleigh fading. But
there's actually many different kinds, and the interesting thing is that they are very much the same. It's just that they use entirely different terminology. So unless you are familiar deeply with terminology, you might not recognize these changes. So
but that's a good
if
point,
you take I will talk now briefly about 4 models. So let's start with swirling 1 and 2. Both of these ones are Rayleigh fading. Then it sort of makes sense that if the object that you bounce your signal on in radar is like an object that produces multiple paths, you get some Gaussian signal variations from it, and then that should be described by Rayleigh fading. And then if you take the strength of that, you get an exponential distribution, which you can also call a chi-square distribution with 2 degrees of freedom. And that is what the terminology that they use in the swirling 1 and 2 models. So it's just Rayleigh fading, but with a different terminology. Then why do they call it 1 and 2? Well, this boils a little bit back to what we talked about before with how quickly is fading happening. We talked about outage capacity versus ergodic capacity. And in swirling 1, you will only see 1 fading realization while you're sending your radar pulse. And then in the 2, you see many realizations, so it changes rapidly, which will describe that the object that you are looking at is changing quickly.
Right, so that rings a bell. I mean, the swirling 1 is basically slow Rayleigh fading, and the swirling 2 is the fast fast Rayleigh fading.
Right.
So you said there were 4 in total swirling models. Which ones are the others?
Yes. So swirling 3 and 4, these are essentially what we call Rayleigh fading. So you have a one strong path, like there's a reflection on it, and then there is some diffuse scattering around these things. And this, in communication, we usually use Rayleigh fading to describe this. But then if you have ever done some mathematical analysis with Rayleigh fading, you discover that it's kind of awkward to try to do that. It's complicated. So therefore there is an approximate version of it called Nakagami fading, which is instead of using the exact model, you describe the power of it as a chi-square distribution, but not with 2, but 4 degrees of freedom. And that is what you use in the swirling 3 and 4 model. So,
that's what you use in the swirling 3 and 4. So they approximate the Rayleigh distribution, essentially.
And then 3 and 4 is once again, then, is it this fast or slow fading?
I see. Interesting, yeah. So this is a nice point, I think, to make that connection between the radar literature, which is also, by the way, very extensive and goes back way long back in time, perhaps even before the wireless comms. I'm not totally sure, but yeah. Great. All right. So you got a lot of chapters, Emil, and most of them are about communications using MIMO, but there's one at the end on reconfigurable surfaces. And although this is in the book is just a single chapter, it looks like you considered it important enough to also put into the title of the book. So what do you think is the role of these surfaces, or will be in the future, and how is it you consider it so important that it goes into your book title?
I think it is important from the perspective that there is no fundamental textbooks that are really covering this. You can find radar textbooks and you can find MIMO textbooks, but covering this topic in non-research literature is basically missing. So that's why I wanted to put it into the book. Then I realized that you can build upon a lot of the things that you have already in the book for MIMO communication. Because if you consider a scenario with a reconfigurable surfaces containing many small elements that reflects the signal, you have a transmitter and you have a receiver, then it's like you have a multi-antenna channel from transmitter to the surface, you have a multi-antenna channel from the surface to your receiver, and then when you combine these things mathematically, you get your RAS channel model.
That's right. So basically, you're viewing this RIS, let's call it reconfigurable intelligence, is RIS. Or do you say reconfigurable surface? It would be like RS or something then, but I'll call it RIS anyway. So you're basically viewing the RIS as a kind of a passive massive, passive massive MIMO base station that just scatters back the information. Of course, much of the MIMO theory would be applicable there.
Exactly.
Although the challenge is, of course, that the path loss doubles or squares.
Yeah. So all the geometry that we have described related to line of sight scenarios with array response vectors and the radar cross section is there because every element is like a reflection of that. You essentially tune your radar cross section by optimizing how this passive surface is reflecting signal. All of those things you can build upon and write something that is relatively short, even if it is kind of deep in the book still.
Right.
And in a way, one can say the surface operates as an analog beamforming transmitter as well. It receives something from the transmitter and then it is transmitting it in the same ways as an analog beamforming can do as well. And that is why these surfaces are typically only good at taking a signal coming from one direction and reflect it in one other direction. So that is a limitation, but it also means that if you're only using in those scenarios, well, then all of this line of sight relevant theory is also very relevant when analyzing them.
That's right, indeed. Yeah. Oh, well, that's great, Emil. Is there anything else that you want to add here as a selling point? So I noticed that one thing where, I think just like in, our book for that matter, but a lot of modern books and communications, they all start off with a discrete time signal model and a discrete time channel models, essentially modeling the channel as a linear time invariant system in discrete time, and on top, which is of course fine if you sample with a Nyquist frequency and so forth. But on top of that, you also adopt, I think throughout the text, if I'm not mistaken, a block fading abstraction, where you essentially say that, by the way, we do the same in our fundamentals book, but you essentially say that, look, we got a time frequency domain, and we can chop this into chunks that you call, I think, a coherence blocks or coherence intervals. Some folks like to call them resource blocks. I think coherence block is or coherence interval is a better term. And that within a coherence interval, the channel is static, so that there's no change in channel gain when you move from the left to the right over time, or when you move from the lowest frequency carrier to the highest. And I think that block fading abstraction is totally fine for all the exercises that you and me have been doing in our books and computing capacity bounds and all of that, because there's an implicit assumption here that we can receive during multiple coherence blocks that sit adjacently and interpolate the channel response among them. So basically it's sampling the time and frequency variation of the channel with a Nyquist frequency and then interpolating. So I think that's totally fine, but what I think ought to be pointed out is that this is the block fading abstraction, while it is super useful for capacity analysis, for building intuition, for a lot of tasks like power control and maybe, scheduling algorithms and this and that, it's completely useless for practical signal processing, because practical signal processing does not work this way. Practical signal processing must interpolate the channel response across multiple blocks. Otherwise, I think with the convention you adopt, I think we use the same conventions here, that within a coherence block, the phase is allowed to rotate halfway around the unit circle when you move from one end to the other, which means that the channel estimate you got at the beginning is completely useless when you come to the end, unless you interpolate. So there might be one thing that I would like to add to this discussion. I think we started off with really asking, like, how should we teach wireless comms, and what are the important things that we want to make sure that our wireless engineers, the fresh-baked engineers, understand. And one more time, the block fading abstraction is totally useful for understanding a lot of phenomena, but we should keep in mind that actual signal processing algorithms have to interpolate the channel. Is that something that you want to rebut on, Emil?
So we are using the block fading model at some places here, and then I think the point is also that how big one should call something a coherence block is very vague. So one can do this kind of rule of thumbs, and we inherit someone of these rule of thumb from previous textbooks, and some of them are making them bigger than others. So one can either try to stretch the sizes of them, and then you would have to interpolate as you're saying, or one can be very conservative and say that our coherence blocks are really small, so that the phases can only vary with at most 30, 45 degrees or something like that. Then you might have something that is a little bit more piecewise constant.
You're totally right. I mean, the definitions are arbitrary, and one could adopt the definition where a coherence block is really tight or really small, so that the phase doesn't rotate more. You mentioned, I think you said 30 or 45 degrees, but I would think even with 30 or 45 degrees, for multi-user MIMO beamforming with zero forcing, if you're 45 degrees off in the phase, I mean, with maximum rate, it doesn't quite matter, but with zero forcing beamforming, it matters a lot. So anyways, this is a technicality, but
yeah, it's an important thing in practice, and I think it's illustrated the fact that, of course, even if you try to write a textbook that is pointing out the most important things, there will always be some things that you have abstracted away in order to provide a simple enough story. So there are more things to learn.
Yeah, indeed, there is. Great. So, yeah. With that, Emil, thanks a lot for this conversation.
Yeah, thank you very much.
That's been really fun and educational. And any new book projects in the pipe?
No, I think I need to take a break for a while now, but I hope that people will take this opportunity to download the book and read it. And if you are using it for your students, if you're a teacher, then we also have full solutions to the exercises that we can share, but only to you as a teacher.
Oh, wow, that's really useful with exercises, also with solutions. So thank you for that, Emil, and bye-bye.
Bye-bye.